Okay, let's be honest, the word trigonometry probably gives you flashbacks to high school math class, right? But what if I told you it's so much more than just a bunch of dusty triangles? Today, we're going to pull back the curtain and reveal the really elegant, powerful idea at its core. Think about it. For centuries, this was the answer to questions just like these. Trigonometry is a toolkit for measuring the world. It's like a mathematical GPS that works by understanding the simple, predictable patterns between angles and distances. So, where do we start? Well, with a shape we all know and maybe love, the right-angled triangle. For a really long time, this little shape was pretty much the entire universe of trigonometry. And the key to that toolkit is probably a word that's still rattling around in your brain somewhere, SOH CAH TOA. It's just a simple set of rules, right? It tells us that for any angle in a right triangle, the ratio of its sides is always going to be the same. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Simple. So let's see how this actually works. Say a ship is traveling north 50 degrees east, and it ends up 10 nautical miles east of where it started. We can draw a triangle, find the 40-degree angle inside it, grab the cosine ratio from our toolkit, and boom, solve for the distance. It's a really reliable, powerful system. But here's the thing. This trusty toolkit, it has a breaking point, a place where it just stops working. What happens when we push that triangle to its absolute limit? And this is the big puzzle. Your calculator will tell you, no problem, that the sine of 90 degrees is 1. But how? If one angle is 90 degrees and our triangle already has a 90-degree angle, well, the opposite side becomes the same thing as the hypotenuse. You'd be dividing a number by itself, which is 1, sure, but you can't even form a triangle to measure in the first place. It doesn't make sense. You can see it right here. A normal triangle? No problem. But the second you try to make that other angle 90 degrees, poof, the whole thing just squashes flat into a line. The very idea of an opposite side and a hypotenuse just completely falls apart. Our triangle toolkit is broken. So to fix this, to solve this little paradox, we have to zoom out. We need to realize that the triangle, well, it was never the whole story. It was just a piece of a much bigger, much more elegant picture. And what is that bigger picture? It's this. The unit circle. A perfect circle with a radius of exactly 1. This is the real home of trigonometry, and this is where it all starts to click. Okay, this is the game changer. Forget about ratios of sides for a second. Instead, I want you to think of sine as just the vertical height. It's the y-coordinate of a point as it moves around the circle. Yeah, the triangle is still kind of there, tucked inside, but the circle is the really fundamental thing. Exactly. And you don't have to take my word for it. I love this quote from a Reddit explainer. You start with the circle, and SOH CAH TOA just becomes this useful little trick that works for the first part of the circle. It's a total flip in perspective. So let's take a little trip around this circle. Watch the point. When we're at a 30-degree angle, look at the height of that point. It's y-coordinate. It's exactly 0.5. All right, now let's keep going up to 60 degrees. See how the point is getting higher? Well, that means the y value, the sine, is increasing too, up to about 0.866. And here it is, the moment of truth. What happens at exactly 90 degrees? The point is right at the very top of the circle. And what's its height? It's the full radius, which is 1. No weird triangle, no dividing by 0, just a simple coordinate. The sine of 90 is 1. Mystery solved. So what just happened? We didn't break math. We just leveled up our definition. It's kind of like how you first learn multiplication is just adding something over and over, right? But that doesn't work for fractions. So you learn a better, bigger definition, scaling. The unit circle is just the grown-up version of trigonometry. Okay, so now that we've unlocked this bigger idea, let's see how it's used to solve some absolutely incredible real-world challenges. And it turns out it's used everywhere because these functions are all about rotation and waves. They are basically the language of modern engineering. You're talking about forces in a bridge, the AC current in your walls, the path of a spacecraft, even how a robotic arm moves. It's all trigonometry. And it's not just for things you can touch. It even describes things we can't see, like sound waves. That smooth repeating up and down of the sine wave is the perfect blueprint for all kinds of vibrations that literally shape our world. So here they are, the key values from our little trip around the circle. This isn't just a random table of numbers, you guys. This is like
a cheat sheet for the fundamental geometry of our universe, from 0 all the way to 90 degrees.
All right, for our last little piece of the puzzle, let's look at something really cool. The names themselves. I mean, sine and cosine. Where did those weird words even come from?
Well, the story is pretty wild. It's basically a 1,000-year-long game of telephone. It started in ancient India with the word ja, which means bowstring. Makes sense, right? Arabic scholars picked it up as juba. But centuries later, European scholars translating the Arabic texts misread juba as a different word, job, which means cove or bay. So they translated that into the Latin word for cove, which is sinus. And sinus eventually became our word sine. All because of a mistranslation? So what about cosine? Well, that co at the beginning isn't there by accident. It's literally short for complement. The cosine of an angle is the sine of the complementary angle. Remember how the two sharp angles in a right triangle always add up to 90? They complete each other. It's such an elegant little connection hiding right there in the name.
And there you have it. That's our deep dive. We started with a simple triangle, ran into a wall, and then used a circle to unlock this whole beautiful, powerful system. It really makes you wonder, doesn't it? What other fundamental shapes are just sitting there, hiding incredible ideas, waiting for us to ask the right questions?